So shall we start? Hello. Today I will give the lecture in place of Professor Lebudek. And today we will see the theory of congestion control in the internet. So what do you see in this picture? In this picture? So it's traffic jam, yes. You see congestion in an intersection. So this is an intersection from Paris. It's not just traffic jam. So it's basically, it's interblocking. So one car blocks the other. So we see that, just a minute. So we see that this car blocks this car, is blocked by this car, which is blocked by the other car. So everyone blocks the other. So and no one can move, basically. So the analog in the internet can be a router or a link where we have too much traffic and the throughput reduces a lot. So in this case, we don't just have congestion, because in congestion, so this intersection could have, for example, a capacity of 10,000 cars per hour. But the traffic here is much more. So if we just had congestion, we just go above, the traffic goes just above the capacity, above, for example, 10,000 cars per hour. So they're not able to pass from the intersection altogether. So queuing starts, and due to queuing we have some delays. But here we have something more. We have too much traffic, and therefore the throughput and the capacity becomes very small, goes to zero, which is not what we want. So what we want is when we have too much traffic, we want to have more throughput, but this is not the case. In the analog case in the internet, in a router or a link, when we have too much traffic, we can have the same thing, and we can have what we call congestion collapse. So in this lecture, we will see congestion collapse. We will see this problem, we'll study this problem, and then we'll propose a solution for the congestion collapse, which is congestion control. And we will see also the different forms of fairness that are achieved by the congestion control algorithms. So the first of one series of congestion collapses that happened in the internet was in 1986, where the throughput from the Berkeley lab to the University of Berkeley, which are two sites that are very close to each other, separated only by 400 yards, became very small. So it became from 32 kilobps to 40 kilobps. And therefore, we found out that we need congestion control in the internet. So let's study a simple example. In this network, this is a small network where we have two sources, S1 and S2, and two destinations, D1 and D2, and two routers in the middle. S1 wants to send to a D1, and S2 wants to send to D2. We assume that these two sources are greedy, which means that they send as much traffic as they want. Of course, they cannot send more than that it is determined by their physical connection to the network. So this source cannot send more than 100 kilobps, and this one cannot send more than 1,000 kilobps, because in a different case, they will have some problem in the network adapter, the Ethernet adapter to the network, and their operating system will adapt the rates. So these greedy sources in the internet can be UDP sources. Also, so these sources send as much as they want. So in this network, we will have links with different capacities. So this link has a capacity of 100 kilobps. This one has one of 1,000 kilobps. This one 110 kilobps. The fourth link here 100 kilobps, and the fifth link has 10 kilobps. We observe here that since the sources send as much as they want, the submitted traffic to this router, which will be the sum of the traffic submitted by source S1 and the traffic submitted by source S2, so 1,100 kilobps, is 10 times more than the capacity of the output link. So in this case, we will have some losses. Initially, the queues of this router here will start to become to increase, to have some packets, because the input traffic will be more than the capacity of the output link. But then, when the queues get full, we will start having losses. We assume that in this case the losses are perfectly fair and they are proportional to the submitted traffic by each link. Of course, this is a highly academic assumption. It's true only when we have a large number of flows or when we have things like TCN and RED that you will see in the next lecture. It might not be true when we have a few number of flows where we may have synchronization issues. So here, since the submitted traffic is 10 times more than the capacity of the output link, of course we will have 90% of the traffic will be lost. We assume also that the links are fully utilized, which is also a highly academic assumption. Okay, so based on what we described, what is the traffic that reaches the destination D1 from the one submitted by the source S1, from the one submitted to the network by the source S1. So I will open the poll. Okay, so the answer is 10 kilobps, and we will see why. Since the submitted traffic to this router is 1,100 kilobps, and the output link has a capacity of 100. Oh, sorry, this is not the answer. Just a minute. And the output link has a capacity of 110 kilobps. So, in order to compute the accepted the ratio of traffic from this link to this link here, we will divide the capacity of the output link with the submitted traffic. So it's 110 kilobps divided by 1,100 kilobps. So it's 10%, and the 90% of the traffic will be lost. Since we assume that the losses are perfectly fair and they're proportional to the submitted traffic, we will apply this ratio of accepted traffic to the traffic submitted by source S1. So the ratio of accepted traffic from S1 at this point here, at point 1, is 10% multiplied by 100 kilobps, so it will be 10 kilobps. At the point 2 here, all the traffic will pass because the capacity of this link is 100 kilobps. The ratio that is submitted by this source, the traffic that comes here at this point by source S1 is 10. So there is enough capacity on the output link. So 10 kilobps will reach finally the destination D1 from source S1. This is an important quantity because it's an information theoretic capacity. So it's what the source sends minus the losses in the network. That is what arrives finally to the destination for this flow. Let's see what happens now with the second source, with source S2. So the source S2 sends 1,000 kilobps. So we apply at this 1,000 kilobps the 10% ratio of accepted traffic. So 100 kilobps from this source will make it to this link. So we see that the sum of the traffic at this link equals to the capacity of the link. Then at the third point, we see that the submitted traffic by source S2 is 100 kilobps, whereas the capacity of this link is 10. So this means that we have again 10 times more traffic submitted to this router than the capacity of the output link, which means that there will be again 10% ratio of accepted traffic. We divide 10 by 100. So it's 10% ratio of the accepted traffic, which applied to 100 gives 10 kilobps. So this is the traffic submitted from S2 that will arrive at D2 finally. So what we see in this example is that both sources send too much, and they send as much as they want. They are greedy, and finally they both are. What arrives at the destination in both cases is only 10 kilobps. They send much more, but what arrives at the destination is only 10 kilobps, and the rest is lost. However, if they had some information, then this source could still send at 10 kilobps. So if this source was sending at 10 kilobps, this source could send at 100 kilobps, because this cannot send more because there is this link here that has 10 kilobps capacity. So even if it sends more, it will not. This traffic will not make it to the destination, all of it. So this will still can have a throughput of 10 kilobps, and this can send 100 kilobps because this link has enough capacity. Here there is enough capacity because it's 100 kilobps and 10, so 110 kilobps, and this link also has enough capacity. However, the problem is that this source here sends too much traffic, S2 sends too much traffic that is lost while it travels in the network, is lost, but it damages the traffic sent by the other sources. So it damages the traffic sent by source S1. So the lesson learned is that if the sources are greedy and they send too much traffic, then there will be inefficiencies. So the links will get full with traffic that will finally get lost, and we will have inefficiencies that benefit no one. So it's the same as the intersection in the roads, in the streets, that when there is too much traffic and there is no upstream control of the vehicles, everything gets blocked, and the capacity and what comes out of the intersection is almost zero, so much less than the capacity of the intersection. So this is what we call congestion collapse. So what we call congestion collapse is that is when the sources send too much traffic and the throughput is very, very small compared to the traffic sent by the sources. So we see now a more complicated example. We see a ring topology. So in general, if you want to create a small network, distribution network, you will make a star topology. But if you want to have a little bit of redundancy, then you can achieve this by a ring topology, where if, for example, a link fails, then the shortest path routing can find a path on the other side of the ring, so you have a little bit of redundancy. In this topology, we assume that everything is symmetric, so that we can have tractable analysis, mathematical analysis, and closed-form solutions. So we assume that every node has a source that sends with rate lambda. And the destination of this source is 2 nodes away, 2 hops away. So for this source here, I, the destination will be here, the node practically I plus 2. So in this node, we also have a source with destination this node here. In this node, we also have a source with destination this one here. And they all sources send with rate lambda. So practically, every source uses just 2 links in the network. And each link is used by 2 sources. So it's used by the source that is directly connected to the link here and by the previous one. So now the source sends the traffic with rate lambda, but maybe not all the traffic can make it to the destination. It depends on the capacity of the links. Here we assume that the link have capacity C, but the relation between C and lambda will determine if the traffic will make it to the destination or not. So if C is not enough, then we will have the traffic that submitted by the source I, only a part of it will pass through this node. And let's say that is lambda prime, what passes through this node. So lambda minus lambda prime will be the losses here. And in the same way, at this node here, we have another source that sends with rate lambda. So here we may have again congestion, and we may have some losses depending on the capacity, on the value of C. And not all of the lambda prime will make it to this link here, but lambda 2 prime will finally make it to this link from lambda prime. So source I sends with rate lambda, but at the destination, what comes out at the destination is lambda 2 prime here. Here we assume that we don't have any competition. What manages to make it to this link just go out of the destination. It does not continue here. It just go out of the destination. There's no competition. So this is lambda 2 prime is the throughput achieved by for this flow, for this source and this destination. And it's the same for all pairs of sources and destination that we have in this topology, which is this node with this node and this node with this node, etc. So if the capacity, because we said that each link is used by two sources. So the traffic, if the capacity is higher than 2 lambda, then all traffic will manage to make it to the destination. So the throughput, lambda 2 prime, will be equal to lambda. So what is submitted by the source will finally make it to the destination, because there is enough capacity. But if the capacity is less than 2 lambda, then we will have losses, because there is not enough capacity for all the submitted traffic in the network. And let's see how we will compute the throughput. As we did before, in order to compute the accepted the ratio of the accepted traffic at this at a node I, we divide the output capacity, which is C, to the submitted traffic. The submitted traffic at each node is equal to lambda, which comes from the source that is connected to the node, and lambda prime, which comes from the source that is at the previous node. So the ratio of the accepted traffic is equal to C divided by lambda plus lambda prime. In the previous example, we divided 110, which was the capacity of the output link, to the submitted traffic, which was 1,000 plus 100, so 1,100. So we assume again that the losses are perfectly fair, and so they are proportional to the traffic submitted by each source. So we apply this ratio of accepted traffic to lambda that is submitted by this source to find lambda prime. So lambda prime equals to C to the ratio of the accepted traffic, C divided by lambda plus lambda prime multiplied by lambda. Then, at this node, again, the ratio of accepted traffic will be the same, because the traffic submitted at each node is the same. We have a completely symmetric setting. So we apply this ratio of accepted traffic to lambda prime, and we find lambda 2 prime. Okay? So this, the first relation is very easy to solve. Everything is known except from lambda prime. Lambda and C are known. So it's a polynomial of second order, polynomial equation of second order degree. So you can solve it with respect to lambda prime. And then if replacing this lambda prime to the second equation 2 here, you will find lambda 2 prime. Okay, any questions until now? Okay, so let's see the graph that comes out of this relation. So here in this diagram, we see we see the throughput from a source to a destination, lambda 2 prime, with respect to lambda, which is the traffic submitted by the source. So we see that, and here we see the value of the capacity is 20. So the capacity divided by 2 is 10. And we compare lambda with the capacity divided by 2 because each link is used by two sources. So if lambda is less than 10, then there is enough capacity and all traffic submitted by the sources will reach the destinations. So lambda 2 prime is equal to lambda, and we have this diagonal here. If now the capacity is the lambda is higher than 10, higher than the half of the capacity, then the throughput, lambda 2 prime, will decrease as lambda increases, according to this relation, which derives by solving the previous equation for a value of capacity that is less than 2 lambda. So we see here that if the source sends with traffic 10, with rate 10, sends traffic with rate 10, then the output at the destination will be 10. But if the source sends with rate 100, then the output will be 3. So it sends more, and the throughput, what comes out at the destination, it becomes much less. And let's see now what happens when lambda goes to infinity. So we will use this relation, this limiting development with the asymptotic extension here, and we can use this relation to replace this term, and we will find that lambda 2 prime is of this form. Okay, so if lambda goes to infinity, we see here that lambda 2 prime goes to 0. So the useful work, it goes to 0. So when the sources send too much, the throughput, finally goes to the destination, it becomes very small, becomes close to 0. So, So what's learned, the lesson learned is that we studied we saw what is congestion collapse, which is when the sources send too much traffic and the throughput decreases a lot, so goes close to 0. And the operating systems today are not made for greedy sources that can send as much as they want. So the sources should adapt their rates in order to the network. They should adapt their rates to the network conditions. Otherwise, we will have inefficiencies, and we will have also congestion collapse. And this happened also in the old internet, where we have a small number of links, and the capacity was only a few kilobps at each link, and we had a small number of nodes. And even then, in 1986, congestion collapse happened. So it's something. So that's why we should develop some congestion control mechanisms to manage and adapt the rates of the sources to the network conditions. So what we saw now is the cost of anarchy. So when sources send as much as they want, and everyone does what it wants, there are inefficiencies that benefit no one, and everyone gets very poor performance, very poor throughput. So therefore, we should develop some congestion control mechanism, and we should determine the rates of the sources that are suitable for the network conditions. This can be cast as an optimization problem. So we can formulate an optimization problem in order to determine what the rates of the sources should be. But what would be the objective value of this optimization problem? So one possible solution is to maximize the throughput in the network. This means being maximally efficient. So we can develop an objective that maximizes the throughput in the network. So let's see this network here, where we have one flow that is the red flow that has a rate x0. The blue flow that has the rate x1, and 9 green flows that each one has a rate x2. So what is the maximum throughput in this network? Any answers on this? No. Okay, so the maximum throughput in this network is 20, and we will see why. Sorry. Okay, so the total throughput in this network is equal to theta, which is x0, the rate submitted by this traffic, by this flow, plus x1 plus 9 times x2. So we want to maximize this throughput subject to the capacity constraints, which means that x0 and x1 should be less than 10. And x0 plus 9 times x2 should be less than 10. We have a capacity constraint on each link. So each link has a capacity of 10 megabps. Of course, the rate should be higher than 0 because they are physical quantities. So we can apply linear programming to solve this problem, but we can just see the solution by inspection. We see that the throughput cannot be higher than 20. Because of course the capacities of the links of each link are 10. So if we add them is 20. So we cannot have a throughput higher than 20. And also we can find an allocation that achieves the maximum throughput. And this allocation that achieves the maximum throughput is the one that assigns at x2 10 divided by 9 megabps, and at x1 10 megabps. Okay. So the maximum throughput, so we find an upper bound for the maximum throughput, and also we find an allocation that achieves this maximum throughput, so the maximum throughput will be 20. Okay, so, and what is the value of x0 that is achieved when we have the maximum throughput? So this is easy. Yes, so it's none of the above. and is 0, as I said. And let's see it. So we want to find the value of x0 when we have this capacity constraint. So x0 and x1 should be less than 10, x0 plus 9 times x2 should be less than 10, and also we have the maximum throughput. So the total throughput will be 20. So from 1 and 3, we can easily find that 9 times x2 will be higher than 10, but from 2, we have that 9 times x2 is less than 10. So x2 will be 10 divided by 9, and then of course x0 will be 0. Okay? So we saw here that we found an allocation that achieves the maximum throughput in the network and it's maximally efficient, but in order to achieve this, we completely shut down one source, one flow, which is x0. We assign the value of 0 rate to this flow. Which might not be socially optimal and might not be desirable. So we want to find some better allocation. This might not be the socially desirable allocation. So we see now the notion of Pareto efficiency, where an allocation of rates, x, where x is a vector that has length equal to the number of sources or flows in the network, if you assume one flow corresponds to one source. And xi, its entry of the vector, is the rate that corresponds to the source, to its source. So a Pareto efficient allocation is a feasible allocation. Feasible allocation means the one that is according to the capacity constraints of the network. And in this allocation, it is Pareto efficient if we increase the rate of one source, then we should decrease the rate. There is one other source for which we should decrease its rate. Okay, so if we see it in a more formal way, so x is a Pareto efficient allocation if for any other feasible allocation x prime, if there exists an I for which at x prime the rate is higher than at x, so if there exists a source I that with higher rate at x prime than at x, then there should be a source j so that it has a smaller rate at x prime than at x. So in order to increase the rate of one source, we will decrease the rate of another source. This is a Pareto efficient or Pareto optimal allocation. So in our example, in this network, the feasible allocations are the ones that satisfy the capacity constraints. So x0 and x1 should be less than 10, and x0 plus 9 times x2 should be less than 10. But the Pareto efficient allocations are the ones that satisfy the capacity constraints with equality, and we will see why. So another question. Which of these allocations do you think that they are Pareto efficient? So you can choose either A, B, or C, or both, or each pair of them, and all of them, or none of them. Or you don't know. Okay, so most of you chose Z, which is the correct answer. So all of them are Pareto efficient, and we will see why. No, sorry. So it's 21. Okay. So we discussed that the Pareto efficient allocations are the ones that satisfy the capacity constraints with equality. And here is the proof for that. Let us assume that that we have an allocation that does not satisfy one of the two inequalities with equality. So we have one strict inequality. So in this case, let us assume that 1 is a strict inequality. So in this case, we can increase x1, we can increase the rate of source 1 without impacting the other sources. So it's possible. So therefore, this is not a Pareto efficient solution. This is not a Pareto efficient allocation, because in the Pareto efficient allocations, if we increase the rate, if we do a change and we increase the rate of one source, then we should decrease the rate of some other source. So this is not a Pareto efficient allocation. If now the second inequality is satisfied, is a strict inequality, and then similarly we can increase the rate of x2 without impacting the rates of the other sources. So this is not again a Pareto efficient allocation. But if we have both inequalities satisfied as equalities by the allocation that we have computed, then if we want to increase x1, we should decrease x0, and similarly, if we want to increase x0, we should decrease x1, and if we want to increase x2, we should decrease x0. So any change, any increase that we want to make, we should decrease the rate of some other flow, and this is a Pareto efficient allocation. So in the previous question, all the allocations, A, B, and C, satisfy the constraints with equality, so therefore they are all Pareto efficient allocations. And we've seen that the Pareto efficient allocations are those are feasible allocations that use maximally the resources of the network here, because the constraints here are satisfied with equality, so they fill the capacities of the links. So the take-home message here is that having a maximally efficient allocation, the one that achieves the maximum throughput, is a Pareto optimal allocation. It uses maximally the resources of the network. However, we completely shut down one source here, x0. We put it to 0 in order to achieve the maximum throughput. And therefore, this is at the expense of fairness, because we're not fair. We completely shut down one source, because actually it uses more resources in the network than the other flows. So it uses 2 links, whereas the other flows use 1 link. And therefore, in order to achieve the maximum throughput, we completely shut down this source. And this is not fair. It might not be socially desirable. So we want to find Pareto efficient allocations that use maximally the resources of the network, but they achieve some form of fairness. In order to do this, we need first to define fairness, to see some definitions of fairness. So we start by egalitarianism, where, according to this definition of fairness, we should allocate as much as possible to all sources, to all flows in the network, but the same to all. So they all have the same rate, but as much as possible, as it is determined by the capacity constraints of the network. So in this example, in the same network that we have seen before, what do you think, which one of these do you think that is the allocation that is according to egalitarianism? I'm opening the poll. And the correct answer is B, as most of you replied. So let's see the solution. So we want to assign the same to all. We want to assign x that is the same to all, subject to the capacity constraints. So 2 times x will be less than 10, and 10 times x, because here we have 9 flows of x0 rate, and 1 flow of x2 rate, and 1 flow of x0. So we will have 10 times 10, because x0 and x2 are equal to x, all the same now. So 10 times x would be less than 10. Of course, x would be higher than 0. So the solution of this system is 1. So the correct answer was 1. So all sources get rate equal to 1 megabps. But this is not Pareto efficient. So this allocation that derives by egalitarianism is not Pareto efficient, because it does not use maximally the resources of the network. So a better allocation would be to give 1 to source 0, to x0, 9 to x1, and 1 to x2. And this is a Pareto efficient allocation, because all the constraints are satisfied with equality. Whereas in the previous case, that x1 had the value 1, in the case of egalitarianism, we could increase x1 here without impacting the other. So it was not a Pareto efficient allocation. Here it is a Pareto efficient allocation, and this allocation also does not give to anyone less than egalitarianism does. So it gives to all as much as egalitarianism does. And this is the maximum fair allocation that we will define more formally now in the next slide. So an allocation X is a maximum fair allocation if it's feasible, of course, and it satisfies this here, which means that for any other feasible allocation X prime, if there is a source that has a higher rate at Xi than at X prime than at X, so Xi prime is higher than Xi, then there should be another source J that has a smaller rate at X prime than at X, And also, at the initial vector of allocation x, xj had a smaller rate than I. The j has a smaller rate than I, so xj was smaller than I, or equal to I. So this means that a max-min fair allocation, an allocation is max-min fair if, in order to increase the rate of one source I, we should decrease the rate of some other source that is richer than I. So it's at the same level or less than I in terms of rate. And so this is a principal definition, and we define max-min fairness in terms of some principles of fairness that we accept. And it's max-min fair, and allocation is max-min fair if any rate increase, if we try to increase any rate, it contradicts fairness, and we should decrease the rate of another source that has initially a smaller or equal rate to the source that we increase its rate. Okay. So let's, based on the definition, let's try to answer which one of the two you believe it's a max-min fair allocation. It's easy, we just discussed. So most of you replied B, which is the correct answer. And we will see now the solution. Okay. So the allocation is not a max-min fair allocation because we can increase x0 to 1. And then we can decrease x1 to 9 and decrease also x2 to 1. And this doesn't contradict fairness because we increase the rate of one source and we decrease the rates of the other sources. However, the other sources were richer initially than the source x0, so that this doesn't contradict max-min fairness. Okay, so A is not a max-min fair allocation. The allocation B is max-min fair allocation because if we want to increase x0, we should decrease x2, which contradicts fairness because x2 is at the same level as x0. They both have 1, rate equal to 1. So if we want to increase now x1, we should decrease x0, which contradicts fairness because x1 is richer than x0. So we cannot do this move. And if we want to increase x2, we should decrease x0, which is non-richer again than x2, so this contradicts fairness. So B is a max-min fair allocation. Okay. So we okay, so the definition of the max-min fair allocation may not be that usable. It may be hard or complicated to apply, but there are some mathematical results, some analytical results for max-min fair that are very useful, and practically all the allocations, in all the cases, in all the networks that we have studied, there exists one unique max-min fair allocation. So if the max-min fair allocation, if it exists, it is unique. Then if we have capacity constraints that are convex in the network, so if the feasible set of rates in the network is convex, then the max-min fair, there exists one max-min fair allocation, so there exists one and it is unique. In our case, we had linear capacity constraints, so we had convex capacity constraints, therefore we had a unique max-min fair allocation. And the max-min fair allocation is Pareto efficient, that it utilizes all the resources of the network. The converse is not true. If we have a Pareto efficient allocation, it might be something else. It might be maximally efficient, not always max-min fair. Okay. And also, the max-min fair allocation can be derived by the water filling algorithm that we will see now after the break. So we'll do a break of 15 minutes and then we'll continue with that. So shall we start? Okay, so we stopped at the maximum fair allocation and the mathematics of the maximum fair allocation. So if we have the set of feasible rates is convex, we have a unique, there exists one maximum fair allocation and it's unique. And the maximum fair allocation is obtained by the water filling algorithm. So let's see this algorithm. We have two sets for the sources, one that are the non-frozen sources and one that consists of the frozen sources. Initially, all sources are non-frozen, and for all the non-frozen sources, we increase their rate at the maximum possible value that is common to all the sources. Then we see which links are saturated, and we analyze all the flows, all the sources that use these links, and we put them from the set of the non-frozen sources to the set of frozen sources. And the frozen sources maintain their rates, and they do not anymore participate in the rest of the algorithm, and maintain the rates that they have up to now. And then we repeat for the rest of the non-frozen sources until all sources become frozen. Okay, so we have now two ways to identify maximum fair allocation. One is to have already an allocation and check with the principal definition if it is maximum fair, as we have seen before. So we check if we increase the rate of one source, do we decrease the rate of some other sources? So we apply the definition. And we use the water filling algorithm. In the other case, we use the water filling algorithm and we directly compute the maximum fair allocation. So let's see the example here. We try to find the maximum fair allocation for this network using the water filling algorithm. So we want to maximize, to allocate T to all sources and find the maximum such T. So all the sources here will have a rate equal to T, and the maximum that value of T will be 1 because of the capacity constraint on this link, that is 10 megabps, and we have 10 flows, 10 sources that use this link. So it's 1. So we see now that this link becomes saturated, and which flows use this link is the X2 ones and the X0 ones. So this becomes saturated, and they maintain the rate that they have until now, so 1 megabps. And still non-frozen source is only X1. And we try to find the maximum increase at each rate, at the rate of X1, the maximum possible. So it's 8 because it already has 1 from this step. And the X0 has 1, so the capacity left is 8. So we can increase the rate of X1 by 8. So X1 will receive 9 at the end. And this link becomes also saturated, so X1 becomes also frozen. And all sources now are frozen, so the algorithm terminates. So the water filling algorithm can last up to the number of steps that is equal to the number of links in the network. So the maximum number of steps of the water filling algorithm will be the number of links in the network. Here we have 2 links, we had 2 steps, but it might be less because we have a finite network, and at each step, one of the links at least will become saturated. And therefore, when all links become saturated, all the flows will become also frozen and the algorithm will terminate. Okay, so let's see this question now. Which allocation is the maximum fair allocation for this network? Okay, so the correct answer is A. We will see the response solution. So we want by applying the water filling algorithm, we want to find the maximum possible increase to the rate of all the sources, but it's common for all sources. So it's we see that it's C divided by 2, and all the links become saturated. So therefore, all the flows of the sources in one iteration become frozen, and the algorithm terminates. So this, the allocation that assigns to all sources the same rate equal to C divided by 2 is the maximum fair allocation in this case. And this example is an example that creates some criticism, that leads to some criticism for the max-min fair allocation, because we see that this flow here, x0, uses all the links in the network, so it uses a lot of resources in the network, whereas all the other sources use only one link in the network. However, they all receive the same rate. So many people think that this flow here, x0, should receive a little bit less rate than the other flows that use only one link each of the network. So that is what led to the definition of proportional fairness. And we see now proportional fairness. So a proportional fair allocation is a feasible allocation if, for any other feasible allocation x prime, this quantity is less than 0. So what is this quantity? Is the sum of the relative changes of the rates of the sources from the allocation x to the allocation x prime relatively to the initial allocation x. So an allocation, in other words, an allocation is proportionally fair if any change to this allocation contradicts proportional fairness. In what sense? In the sense that the total rate of change, the rate of change the rate of change for all sources, we take the sum for all sources, is negative. Okay, and this has two effects. The proportional fair allocation. First, it considers the global effect. So it takes the sum. So it considers a global effect. It considers all sources, which means that if we can decrease just one source for a bit, and then we can probably increase many other sources, and in this case, this sum of the total rate of change will be positive, so it will be an allowable change, a good change. We should do it. And also, the relative shares matter and not the absolute. For example, we divide here by the allocation, the initial allocation x. So the relative shares matter. So for example, if we have a connection of 1 megabps and we increase it by 10 kilobps, it might not be very important. But if we have a connection of 20 kilobps and we have a satellite connection with 20 kilobps and we increase it by 10 kilobps or decrease it by 10 kilobps, then it might be more important. So this is again, the definition of the proportional fairness is again a principal definition, but is based on different principles than the max-min fair allocation. And actually it defines a measure here of fairness. Okay, so if this quantity is negative, then the allocation is proportionally fair. Also, I will tell this later. So, based on these definitions, this discussion, which one do you believe that is proportional fair allocation of the two, or both? They can be both. So I'm opening the poll. So the correct answer is D, none of them, and we will see why. Okay, let's see the first allocation first. We observe here that we can increase by delta is xi for these flows that use only one link, so x1, x2, x3, x4. And we can decrease then x0 by delta. Delta, of course, should be small, should be less than c divided by 2, because so that the new allocation after doing this change is also feasible. And then the total rate of change will be minus delta for x0 minus delta divided by c over 2. Plus 4 times, because we have 4 of them, delta, which will be the change for each one of them, divided by c over 2, which is the initial allocation for each one of them. And this is positive. So we can do this change without contradicting proportional fairness. So it's not, this allocation is not a proportional fair allocation. Okay. So let's see the second allocation. So here we can increase its value. So the initial allocation here is 1 megabps to x0, 9 to x1, and 1 to x2. And we can increase x2 by delta. decrease x0 by 9 times delta. Of course, delta should be small, should be less than 1 over 9, so that the new allocation is again feasible. And we can increase x1 by 9 times delta. And then the total rate of change will be minus 9 times delta for x0 divided by 1, which is the initial allocation of x0, plus 9 times delta for x2 divided by 9, which is the initial allocation for all the 9 flows x2, plus, no, this is the term. This is the term for x2, sorry. It's 9 times delta divided by 1, which is 9 x2 flows. Delta is the change for each one of them. 1 is the allocation for the initial allocation for x2. And here is for x1, which has the initial allocation of 9 and change of 9 delta. Because it increased by 9 delta. So this quantity is again positive. So we can do this change without violating, without contradicting proportional fairness. So this is not again a proportional fair allocation. Okay, any questions? So the definition of proportional fairness, it might not be again very useful, but in order to apply it, but there are some mathematical results for the proportional fairness again, like maximum fairness. So if we have the set of the feasible rates is convex again, so we have convex capacity constraints in the network, then there exists one proportional fair allocation, and it is unique. Now it is Pareto efficient, so it utilizes the resources fully of the network. And the proportional fair allocation can be obtained by maximizing this quantity, so by maximizing the sum of logarithms of the rates for all the sources in the network. And we will see the intuition why. Of course, we should have constraints for capacities of the links of the network, so we should have capacity constraints in this optimization problem. And we will see why, the intuitive explanation. If we want to maximize this quantity, one way is to follow the gradient to reach the maximum. So the gradient of this separable function will be this one. So it's dxi divided by xi. So this is the gradient of this value. And this is very similar to the quantity used by proportional fairness to identify fairness, to quantify fairness. So if we reach the maximum of this function, then any move from the maximum will render this gradient negative. So it's not an allowable move. It's not a good move because we will go further away from the maximum. And this is what is also done by the proportional fairness. So if this quantity is negative, then it's not an allowable move. It contradicts proportional fairness. Okay, so the proportional fair allocation also, because of this optimization problem, because it derives as a result of solving this optimization problem, gave us a new objective function in the optimization problem of determining the suitable rates for the sources in the network, so as to perform congestion control. Because we've seen that maximizing the total throughput, it's not socially optimal. It might not be socially desirable. So this can be another objective for the optimization problem in order to find the suitable rates for the sources in the network that also leads to proportional fairness. So based on, let's now compute the proportional fair allocation for this network. So we will maximize the sum of logarithms for all the sources, so log x0 plus log x1 plus log x2, etc., subject to the capacity constraints of the link. So x0 and x1 should be less than c, x0 and x2 should be less than c, and for 3 and 4 the same constraints. And this can be solved by convex programming, but also we can have a direct solution here, because we've seen that all the constraints should be satisfied with equality. Otherwise, it will not be proportional fair allocation. And this is because if one of the constraints, let's say the first one, is not satisfied with equality, then we can increase x1, and this will give us a higher logarithm of x1, and therefore we will have a better objective function, a higher objective function, So therefore, if we don't satisfy the constraint with equality, is not optimal, and it's not proportionally fair. Okay. So therefore, all the constraints should be satisfied with equality, and therefore we can assign x0 equal to x star, which will be the optimal value of x0, and we can set all other xi equal to c minus x0, because the constraints are satisfied with equality. And then we replace these relations to the objective function, and so from dimension 5, we went to dimension 1, and we can solve this problem. Subject to x star, of course, would be higher than 0 and less than the capacity. And we studied the derivative of this problem. So this is the derivative. We set it to 0. We can compute x star. And then by replacing to this relation here, we can compute the rates for all the other flows, for the other 4 flows. So this is the proportionally fair allocation for this network. So let's see now what is the proportional fair allocation for this network. What do you believe? I'm opening the poll. So the correct answer is D. We can see it by excluding some solutions. So for the first allocation, for A, we have already seen that it's not proportionally fair. For the second allocation, we see that it does not use maximally the resources of the network. It could be better, it could be improved, because x1 can be increased, because this link is not fully utilized, so it's not a proportional fair allocation. The third allocation goes to the wrong direction, because it assigns more to x0 than to x2. And here we see that x0 uses more resources in the network, uses 2 links, whereas x2 uses only 1 link. So according to proportional fair allocation, if we use more resources, then we should have less rates, so it goes to the wrong direction. And so only this D is the answer that is left, and we will explain why it's the proportional fair allocation. So we can solve the optimization problem, maximizing the sum of logarithms for all the sources as before. Again, it's the same as before, so all the constraints, the capacity constraints should be satisfied with equality. Here they're not shown, but since they're satisfied with equality, we assign x0 equal to x star, and then x1 will be 10 minus x0, x star, minus x0, so minus x star, and x2 will be 10 minus x star divided by 9. So we replace it to the sum of logarithms, and we maximize this quantity. And therefore, the solution is 10 divided by 11 megabps for x star, and then we can use this relation to determine x1 and x2, and this allocation is D, is the answer D. Okay, so the proportional fair allocation, it's an allocation that maximizes a global utility function. The utility function is the log of the rate, and each source has a utility function, which is the log of its rate. And the proportional fair allocation maximizes the global utility function, which is the sum of the logs, the sum of the utilities for all sources. So the sum of the logs of rates for all sources. We can take another utility function, not the log, but another utility function, and then have what we call utility fairness, more generally. Okay. So here is the utility, and here is the rate x of a source, and this is the log x. So this is the utility function assigned to a source in order to achieve proportional fairness. And then we maximize the sum of logarithms of rates, so the sum of utilities for all sources. We want to see now what is the relation of maximum fairness with utility fairness, because maximum fairness is not a utility fairness, because it cannot be expressed as an optimization problem. But there is a relation of maximum fairness with the utility fairness, and actually it's the limit of utility fairness when the utility function converges to a step function. Let's see this in more detail. So let's assume that we have this utility function here, which is given by this formula, and we assign the rates by maximizing the sum of utilities for all sources, according to where the utility is given by this formula. And then we repeat this process by increasing m. So basically, we repeat this process as these utilities converge to the step function. Of course, the step function is not a very useful utility function because it assigns just positive utility if we have just positive rate, and the value of the rate doesn't matter. So it's not a useful utility, and we don't say that the maximum fair allocation is the allocation, is a utility fair allocation that uses as utility function the step function, but the maximum fair allocation is the allocation that is the limit of all these allocations that derive by assigning rates with these utility functions as m goes to infinity. So it's the limit. So it's this approximation, but it's useful in order to compare the maximum fair allocation with the proportional fair allocation. So this, for example, could be the utility that corresponds to maximum fairness, and this could be the utility that corresponds to, this is the utility that corresponds to proportional fairness, so just for comparisons. And we will use it, we'll use this later. Okay, so the take-home message is that we should perform congestion control, and the sources should adapt their rates to the network conditions, otherwise we will have congestion collapse and inefficiencies. And we should apply some congestion control mechanism that will be Pareto efficient and will utilize maximally the resource of the network, and also it achieves some fairness, proportional fairness or maximum fairness. Okay, let's see a little bit more on how congestion control is implemented now. So there will be zillions of congestion control mechanisms. We will focus more on the end-to-end congestion control that is used in the internet, where there is not a centrally computed rates that are assigned to the sources, but each source tastes the water, uses some rate, and then depending on the feedback it takes, it either decreases or increases its rate according to some host congestion control algorithm. So it has some congestion control algorithm, and it increases or decreases its rate according to the feedback it receives from the network. In cellular networks, for example, when we have mobile phones that are connected to the base station, then the base station determines the rate of its source based on proportional fairness, usually, and it assigns the rates to all the mobile phones. So if you have a connection of a specific rate, then it's possible that you don't always receive this rate that you have agreed, but you may receive less based on what the base station determined according to proportional fairness. And also in cellular networks, another case would be that there is one queue per flow, and all queues are served with round-robin fashion. And this is also another possible scheme. But we will focus here on the end-to-end congestion control. So before the congestion control mechanism started in the internet, the only congestion control scheme that existed was at the DEC nets, which was using the congestion avoidance bit, or else the DEC bit. So the sources, when they were submitting traffic to the network, they were clearing this congestion avoidance bit, and then the routers were monitoring the traffic that passing through them. And if the traffic was more than they could handle, if they were operating above their knee, then they were setting this congestion avoidance bit. And then the destination, if received this congestion avoidance bit set through the transport layer, the sources were decreasing their rates accordingly. This is how congestion control is performed today, similarly in the internet. So let's study this simple network. So we have a very simplistic model. We have modeled all the network as a single link with capacity C. And we have sources here that submit traffic with rate xi. Each one of them has a rate xi. And then they receive feedback, y of t. So basically, if the sum of the rates for all sources is less than the capacity, the feedback that they receive is 0. Otherwise, if the sum of the rates for all sources is higher than the capacity, then we have congestion, and they receive feedback equal to 1. So if they receive feedback equal to 1, they should decrease their rates in some way. based on their host congestion control algorithm. Otherwise, if the feedback is equal to 0, then they can increase their rate or do nothing. They basically increase their rate. But in how we should define how the sources will increase or decrease, according to which law they will increase or decrease their rates. So we first study the linear laws, which is what we do also when we don't know exactly what to do. So we will do the linear laws. According to them, if the source receives feedback equal to 1, which means that we have congestion and we should have decrease, then the new rate is determined by this linear relation based on the previous rate, where U1 should be less than 1 and V1 should be less than 0, and at least one of the two inequalities should be strict. Less or equal to 1 and less or equal to 0, sorry. And this is U1 is the multiplicative decrease factor, and V1 is the additive decrease term. If now the source receives feedback equal to 0, which means that there is no congestion, then it can increase its rate, and the new rate is determined by this linear law with respect to the previous rate, where U1 should be higher or equal to 1, and V0 should be higher or equal to 0, and one of the two inequalities must be strict in order to increase the rate. And U0 here is the multiplicative increase factor, and V0 here is the additive increase term. So these are the linear laws. Let's see an example with these linear laws. Here we have U1 equal to 0.5, so we have multiplicative decrease, and we don't have an additive decrease term. And each time we receive congestion feedback equal to 1, so each time there is congestion, the new rate will be half the previous rate. And we have additive increase. So U0 will be 1, and V0 should be 1, so we have an additive increase term. So let's see, these graphs here correspond to a network, to a link, where we have three sources. The two sources start immediately, whereas the third source comes later. And the second source has initially a high rate, whereas the first source has a smaller rate initially. And the first source tries to increase, the second source decrease because both of them hit the capacity limit of the link, and so they receive congestion feedback that is 1. So there is congestion, so they decrease their rate to half of the previous rate, and then they start increasing again because they receive 0 congestion feedback, and then they reach again the capacity and decrease again, and this happens. So these oscillations are inherent to this mechanism, and they reach the same level, the same average rate. Of course, there are oscillations because they reach capacity, they decrease, and then they increase again, and this process is repeated, but they have almost the same average rate. And then the third source comes, which is a polite source. It starts with rate 0, and it tries to increase its rate and come to the same level as the other ones. And here we see that these sources also decrease their average rate because when the third source comes and increases its rate, then the three of them reach the capacity at a lower value of rate of S1, of source 1 and source 2. So they also decrease their rate, their average rate. And finally, they all come at the same level. Of course, there are the oscillations because this is inherent to this mechanism, and when they reach the capacity, they receive congestion feedback, they decrease again, and then they increase again, etc. Here we see the average rate when we have the two sources and when we have the three sources, and we see that it's the same in both cases. And here we have a measure of unfairness. So initially, the measure of unfairness has a high value because source 2 has a very high rate and source 1 has a very small rate, and therefore this is unfair. So the measure of unfairness has a high value, and then it decreases to 0 when they come at the same level, and then again it increases because source 3 has a very small rate compared to the other two. And when they come to the same level, and they all come to the same level, the measure of unfairness decreases again. Here the capacity of the link is around 10, so that is why initially source 2 has 10, and we see here that the average rate is around 5. So the capacity of the link, when we have two sources, when we have three sources, is less, is around 3 point something. Okay, so let's see now we saw an example of how these linear laws work. And now we want to determine how the values of the coefficients affect the rates achieved. So what will be the values of the coefficients of the linear laws? We want to achieve efficiency. We want to be Pareto efficient to maximally use the resource of the network, and we also want to achieve some fairness. Here we have a single link, and if you have a single link, the max min fair allocation and the proportional fair allocation are the same, and they assign the same rates to both flows to all flows that use the link. Okay. So we want to determine the values of the coefficients so that we achieve efficiency and fairness. Let's see here an example. This is a phase diagram. So we have two flows. We study only the two flows. And here is the rate of the second flow. Here is the rate of the first flow. And initially, we have a specific allocation that is given by this vector. There is not time explicitly in this diagram, but there is a time trajectory. So this is the initial allocation. Here, the sources receive zero feedback, which means that there is no congestion. So they increase their rate by this vector here, so that the new rate will be the sum of this vector and this vector. Then they receive again zero feedback, which means that there is no congestion, and they increase again their rates by this vector. So the new vector is this one, is the sum of the three vectors here. And at this point, they receive negative feedback. Why they receive negative feedback? Because this line here is the line that determines the capacity. So x1 and x2 equal to c. So when the sum of the rates of the sources is higher than c, so when we pass this line here that determines the capacity, they receive feedback equal to 1, so there is congestion, so therefore they should decrease their rates. So we reached one of our objectives. We reached efficiency. We were close to the capacity of the link. But we also want to achieve fairness. And fairness, in our case, either proportional fairness or maximum fairness, they are the same, and they assign the same rates to both flows. So we want to reach this point. That is where the diagonal line, which is the line that determines that the two rates are the same, and the line that determines the capacity, they intersect. So we want to reach this point because at this point we have both fairness, we have equal rates to both sources, and we also have efficiency because we work close to the capacity. So in this case, so we want to reach this point. So this is how we will determine the coefficients and the terms, the additive terms of the linear control laws. So a question for you. So which either one or two you believe that is additive increase, and which one do you believe that is multiplicative increase of the two? So I'm opening the poll. So the correct answer is A. And we'll see why. So when we increase, we increase the rates, we add a vector that is proportional to the diagonal. So we add the same value to both sources. So we practically add a vector that is parallel to the diagonal line here. So we add something like the vector 1. But when we do additive increase, when we do multiplicative increase, we multiply the initial rate allocation with the coefficient. Therefore, it's like adding a vector that is parallel to the initial allocation. So it's like adding this vector 2 here. So 2 is multiplicative increase and 1 is additive increase. Okay, and let's see now how we will choose the coefficients and terms of the linear laws. So if, let's assume that we have this initial allocation, x, and let's assume that we receive feedback of congestion, so we need to decrease our rates. So we can do either additive increase, which will be like this, and either multiplicative decrease, which will be like this. We observe that with additive increase, in terms of fairness, we become worse because we move further away from this point here, that is where we achieve fairness. Therefore, it's not desirable. We don't want to have additive decrease. So we will do only multiplicative decrease so that we don't go far away from fairness. Okay? Now, for the increase, let us assume that we receive feedback positive, 0. So this means that there is no congestion, so we can increase our rates. So if we do multiplicative decrease, we'll do something like this. And if we do additive increase, this is the only case that we can go closer to our target, which is the point of fairness. So we should always include the term of we should always include the additive increase term. We should always have additive increase. We can have also multiplicative increase, but we should also always have additive increase because that's the only way to go closer to fairness when we can increase the rates. Okay, so therefore, that is why we should use additive increase and multiplicative decrease in order to achieve both fairness and efficiency in the network, so both our objectives. And this is what is implemented in the internet. Sorry. So, what do you think that is the allocation that is what do you think? What form of fairness you believe that is achieved by the maximum fair allocation? By the additive increase, multiplicative decrease. So I will not open the poll, but I will just explain it. So additive increase, multiplicative decrease achieves something between proportional fairness and maximum fairness, and we will explain this. Let us assume that we have additive increase, multiplicative decrease with additive increase plus r and multiplicative decrease given by this factor here, 1 minus eta. And one update is implemented per each time unit. Then it's like implementing utility fairness. It's the same as implementing utility fairness with this utility function given by this form. And if we plot this utility function, is this one, the blue curve here, with some values that are given here. And this is maximum fair, close to the step function. It is approximately maximum fair, it's close to the step function. This is proportional fairness. So we see that it's in between maximum fair and proportional fairness, but closer to proportional fairness. So additive increase, multiplicative decrease, what is used in the internet, achieves something between maximum fair allocation and proportional fair allocation. Okay. And now we will see something more, and we will finish. We'll see just slow start. So additive increase, multiplicative decrease, it's okay. We fixed it. We formulated. We found the coefficients in terms of the linear laws. But it can be. We want to accelerate it more, and we will accelerate it more using the slow start. So slow start is not at all slow. It's actually fast. It's actually fast. It's not slow. This is what happened before. So initially we had source 1 that had some rate, and source 3, and here we have source 1 and source 3. And source 3 came, and they both increased their rate up to the point that they reach the capacity, and so they decrease. Their rates become half of the previous one, and then they increase again, and then the rates decrease, etc. And then they reach here with the additive increase, multiplicative increase, the area that is desirable, that is close to the diagonal, so they have almost the same rate, and it's efficient, it's close to the capacity. However, as we see here, this convergence is slow. So here we have sources 1 and 2 that this is a well-organized system where they both have almost the same rate. And then source 3 comes and tries to come at the same level, but this takes around 5 iterations to finish, to come to the same rate, which is, it's very slow because each iteration might take more than the round trip time, where the round trip time with the old internet were on the order of seconds. So this is not considered as fast. So therefore, that is why slow start is used, in which initially it's used when we start at the beginning, and also when we have some losses that are observed by timeout. And actually, when the source at the beginning, when the source increases its rate, it increases its rate with a multiplicative way. up to a target rate that is assigned initially based on, empirically based on what we observe, what we believe that will be the rate that, that would be able the source to achieve. So we initially assign this target rate, and we do multiplicative increase of the rate of the source until it reaches this target rate or until there is a negative feedback received. So if there is a negative feedback received, then the target rate becomes half of the initial rate. Because if we receive negative feedback, this means that we have congestion. So this means that we are at the same level as the other flows, and we have reached a point close to the capacity. So therefore, the target rate becomes half that it was before, and the rate of the source decreases, and increases again in a multiplicative way until it reaches the target rate, or until it reaches again a point where we receive negative feedback. And we exit slow start when we reach the target rate, not when we reach a point that we receive negative feedback. So when we reach the target rate without receiving negative feedback. This is the algorithm that I just described in pseudocode. And this is what happens with slow start in our previous example. So initially, source 3 is much more aggressive, and it increases its rate a lot. Then they both decrease. Source 2 decreases by source 1 decreases its rate by half, and source 3, because it's in the slow start, it decreases its rate close to 0 at a very small value, because source 3 is at the slow start, it had just entered the network. And then they both increase, and they reach much faster the desirable area that is close to efficiency and fairness. Okay, and we see it here in almost 2 iterations, probably one iteration, they reach the same level, all flows with slow start. So the convergence of the additive increase, multiplicative increase, close to the desirable area of efficiency and fairness, it's much faster with slow start. And this is also the comparison of the two, as we have already seen. And so a summary of today. So that's all for today. And thank you very much for being here, and see you tomorrow at the lab.